When light shines on a metal surface, electrons in the metal absorb the energy in the light. If they absorb enough energy to overcome the minimum energy with which an electron is bound in the surface of the metal, called the work function of the metal, then they can be ejected. We call these ejected electrons photoelectrons, and this effect the photoelectric effect. Now consider dim light shining on the surface of a metal. By dim, we mean low intensity, where, remember, intensity is net power radiated per area, which goes like the amplitude of the electric field squared. Now, Maxwell's classical theory says that light is an electromagnetic wave whose energy is distributed uniformly and continuously throughout the wave. So, according to this classical theory, when dim light shines on the surface, it'll take the electrons some time to accumulate enough energy in order to overcome the metal's work function and be ejected from the metal. So, classically, we'd expect a time lag between the start of illumination and the ejection of the photoelectrons. Let's calculate the time lag we'd predict using this classical theory. Consider the photoelectric effect apparatus, in which the incident radiation has intensity 0.01 watts per meter squared, and the work function of the metal is 2 eV. Estimate the time lag expected from classical physics between light illuminating the surface of the metal and the start of current flow. How does this compare to the approximate time lag measured experimentally? Use 10 to the minus 10 meters as the approximate radius of the atoms in the metal. Let's start by estimating the kinetic energy that an electron in the top surface of the metal absorbs in this process. So we'll call that kinetic energy K. Because we're assuming that the energy in the light is uniformly and continuously distributed, we'll assume that in a time t, each atom in the top atomic layer absorbs an equal amount of energy proportional to the atom's cross-sectional area, A. So if we assume that this is the case, and that the electrons, and that all of this energy goes into an electron in the atom, then this absorbed energy of the electron is given by the intensity of the absorbed light times the cross-sectional area of the atom times the time, where this cross-sectional area is just pi r squared, and we're given the radius of the atom to use in the problem statement. And this intensity is the absorbed intensity, and more generally, it'll be given by some number c times the incident intensity, where c is some number between 0 and 1. So it would be 1 for perfect absorption of the incident light, but less than 1 for less than perfect absorption. Now in the problem statement, we're not told anything about an absorption percentage, so we're just going to assume c equals 1. So that this absorbed intensity is the same as the incident intensity. Also note that the units in this equation make sense. We already discussed in the introduction that intensity goes like power over area, which goes like energy per time times area. So indeed, this right-hand side will have units of energy. Good. So what does our photoelectric effect apparatus actually measure? It measures the maximum kinetic energy of the ejected photoelectrons, which we'll call Kmax. So these are the ejected photoelectrons, and they absorbed this energy, but then had to overcome the metal's work function. They had to overcome the minimum energy with which the electron was bound in the metal in order to actually escape. And so since this is what my device will measure, the maximum energy of these ejected electrons is the absorbed energy minus the metal's work function, where we're given the work function in the problem statement also. So now the question is, so this is the big equation, and now the question is, how much time will it take an electron to absorb enough energy to overcome the metal's work function and thus be ejected? This will happen precisely when this maximum kinetic energy is 0. So this time delay between the start of illumination, which we'll call Td, and the ejection of the electron is precisely when it has enough energy to escape. So we can solve this equation for Td, and we'll get that it's phi the time delay is phi over the intensity times the cross-sectional area of the atoms. Now it's just a matter of plugging in all these numbers that were given in the problem statement, which we can do, and we'll find that this time delay is 17 minutes for this apparatus. So how does this answer match up with experimental results? Experiments show that there is actually no time delay. If there's a time delay, it's less than a nanosecond. So classical physics, where we estimated a 17-minute time delay, absolutely cannot explain the experimental results. Einstein provided the resolution to this puzzle, and it earned him the Nobel Prize. Our wrong assumption before was that the energy in the light was distributed continuously. In fact, the energy in the light is distributed in discrete packets called photons, each of which has an energy of hf, where h is Planck's constant and f is the frequency of the light. Then the kinetic energy that the electron absorbs is actually the energy of the photon that hit the atom. And so the correct description for the maximum kinetic energy of the photoelectrons is hf minus phi. So unlike our classical answer, the kinetic energy of the photoelectrons is independent of the intensity and goes up linearly with the light's frequency, both of which have been observed in experiment. So why is there not really a time delay? Well, dimming the light while keeping the light's frequency fixed means less photons, but the energy in a single photon is still the same. So as long as a single photon has enough energy to eject an electron, then the electron will be ejected immediately.